Welcome to my reading session. Today, let's read about the tile-based programming in RAP 1.5. This is from the official NVIDIA developer blog. Okay, with the latest release of RAP 1.5, developer now can access to new tile-based programming primitives in Python, leveraging CU Blast X and CUFFTDX. These new tools provide developer with efficient matrix multiplication and Fourier transform for the accelerated simulation and scientific computing. In this blog, we introduce this feature and show how they can be used to optimize your application. The tile-based programming model available in RAP 1.5.0 is currently in preview. The performance and API may change in the upcoming version. Now let's do the introduction. Over the past decades, GPU hardware has evolved from purely SIMT, that means single instruction multiple thread execution model, to one that now relies heavily on cooperative operation for increased efficiency. As tensor core math units become larger part of overall GPU compute efficiently and proficiently, productively, productively what is this productivity programming them becomes increasingly important. High level APIs like BLAS offer abstraction that can target wide range of performance low level instruction. However, these APIs are often difficult to integrate with user program and can lose efficiency by, for example, enforcing the result back to the global memory between the library call. Conversely, directly programming tensor cores at C++/CUDA level is complex and demand careful management of data flow between the units. To address this issue, tile-based programming model such as those found in OpenAI Triton and C++-AMP have been developed. Unlike pure SIMT, single instruction multiple thread, tile-based programming allows developer to express the operation on tiles that multiple thread can execute cooperatively, enhancing both efficiency and productivity. With RAP 1.50 release, we extend the RAP kernel-based programming model to tile-based programming, aiming to give RAP developer access to full power of modern GPU hardware. This extension, what does this provide? This extension provides a programming model that allows the developer to smoothly transition from SIMT to tile-based execution, reduce the number of manual indexing, shared memory management, and pointer arithmetic, support auto differentiation for backpropagation and training. Additionally, RAP leverages the CUDA BLAST DX and CUDA FFTDX to implement the matrix multiplication and fast Fourier transform tile operation. Combined with the RAP tiling programming model, this NVIDIA device side math libraries enables seamless fusion of tensor core, accelerated GEMM, NEFF, GEMM, NEFFT, and other tile-based application operation within the single kernel, reducing I/O and kernel launch overhead while maximizing the arithmetic intensity. With this approach, we can outperform the traditional linear algebra or tensor framework by factor of 4x for the required application requiring the dense linear algebra such as robot forward dynamics. What are the now let's get into the RAP tile primitives. The new tile primitives in RAP include the construction, load and store, linear algebra, map and reduce operation, in which they natural extends the existing kernel-based programming model. What is construction? Tile may be constructed inside the RAP using the NumPy style operation, like that like NumPy, we import the first import the wrap as WP, and we give the decorator WP.kernel. That means it is using this decorator WP.kernel, and we are constructing the tile of 0 32 bit using the A is equals to WP dot tile wrap. Oh, it is editable. Nice UI, I think. How did I do it? Oh, double click to make it in editable mode. But I don't think it can be run here locally. That's not long run, but yeah, it can be edited in this block. Let's get likewise. What are we doing? We are creating a new 16 by 16 tile. We are giving m and n dimension of tile, and we are also can also define the data type of the tile. We have WP dot float 32 means floating point 32 bytes bit float. Construct the tile of 16 bit float. Initialize it is 1. Like when we initialize in 0, so we are giving tile dot 0. In initialize 1 initialization of the all the tile, we are giving the tile that we are using the tile dot tile 1 methods. In the wrap, there are 2 dimension arrays. In wrap, there likewise it describe the code. In the wrap, the tiles are 2 dimension array that may contain a scalar, vector, matrix, or structured data types as elements. Unlike wrap arrays or PyTorch tensor, where dimension are dynamic, is specified at around tile dimension. Example: 16 by 16 in the example must be constant that are known at compile time. Not it is the one of the difference between when you define in the NumPy or a PyTorch tensor, it can be determined at runtime, but when programming with the wrap, we have to define it in compile time, and it cannot be changed. Unlike SIMP, which is local to the thread, tile is stored across the entire CUDA block, either register or shared memory. The full list of tile constructs can be found here. Here is the link. And what is load and store? Wrap provide explicit load and store operation for the tile data to and from global memory. These operations are performed cooperatively by all the threads in the block, ensuring efficient data transfer between the global memory and shared or register memory. In the example below, 2 tiles of data are loaded from the global memory, summed together, and results are stored back to the global memory. The user did not need to manage the shared memory allocation or storage accurately. Here what is given, we are importing the wrap as usual. We are also using the wrap decorator as usual, wp.kernel. We are also loading the tile input tiles, 2 tiles m and a6, they are the dimension, computing the sum of these 2 tiles, and we are cooperatively storing in the global variable. And we do not have to explicitly manage the memory when when we do the CUDA programming in C++ system. In addition to the store and load and store operation, this is load and this is store, this is load, this is stored. In addition to this operation, wrap support the atomic operation wp.tile atomic add for full system of the memory. But you can also look at the documentation. I think it has given a nice documentation. Matrix multiplication in tile. One of the key benefits of the tile based programming is the ability to perform the cooperative matrix multiplication. Wrap 1.50 introduces the general multiplicity accumulative primitive wp.tile matmul, which allows developer to perform the cooperative matrix multiplication. Under the hood, this leverages the CUDA bus, which depending on the element type, matrix size, data layout, will automatically dispatch the appropriate tensor core YAML instruction for the best performance. Let's walk through the wrap to perform the matrix multiplication. We are defining a constant. We are allocating the input tile 0. The dimension is tile m and tile n count, and we are iterating over the count. Count is k by tile k, which is 64. Yeah, and we are iterating over the inner dimension. We are loading the tile. We are performing the matrix multiplication and accumulating it in the sum. We are storing the tile. We are this is the one it is given to test the operation of the above function. In this example, we define the gem tile that perform the tile matrix multiplication. The kernel loops over the 2D slice of the global memory, loads them into the shared tile, perform the matrix multiplication using the wp.matmul. Tile matmul accumulates the result in the shared memory, stores the result back to the global memory. The figure shows the performance of the GEMM kernel as a percentage of QBLAS 12.4 on NVIDIA A100 18 GB SXM clock locked to their maximum for the range of FP32 matrix sizes. For small problem, we see the performance is competitive with QBLAS, which may be explained by the fact we have used auto tuning to find the optimal parameter for this small size, because the launch overhead is more significant portion of the cost. For larger problem, performance is lower since currently tile results are stored in the shared memory. For small problem, there is the problem of the overhead issue, because they have to be loaded in the GPU, and it takes some time. But if we are using the for the last computation, that overhead, the beginning overhead, becomes so negligible, and the performance improvement is huge as compared to the before. However, even with this simple example, we see the approximately 70 to 80% of QBLAS performance for the large multiplication. For the future version of the RAP and QBLAS will provide the improved performance by keeping the gems register. What is this gem performance of the register in as the part of QBLAS? Gem size 128, 256, 512, 224, and the performance improvement is above 100%, below 150%. It is nearly 150%, you can say. It is so huge compared to the other. In this picture, we look the effect of this tile size on overall performance for the single problem size. Overall performance is the function of tile dimension, which determine how the problem is decomposed, and the block dimension, which determine how many threads are assigned to each sub problem. Here we see the m is equals to k, n is equals to k is equals to 124 problem. The best performance is obtained using the tile dimension. Tile m is equals to 32, tile n is equals to 64, tile k is equals to 64, and 128 threads. RAP dynamic programming and runtime kernel creation allows user to perform the auto tuning of the hyperparameter as shown in the benchmark script. So this is benchmark script. Now the MapReduce tile 1.50. Let's go through the quick this one quickly. It also introduces the MapReduce primitive, enabling developer to perform the reduction and element-wise operation on tiles. These primitives are essential for the tasks such as layer num and softmax, which require the efficient reduction using the various quantities. The example below shows the compare the sum of the all element in row of the using one block per row and wp.tile sum to perform the cooperative reduction. We are obtain our tile index block in tile index, and load the element into the memory, perform the cumulative perform the sum to the element, store the sum to the tile, and we are initializing the ones and empty, and we are launching the tile. RAP also support the custom reduction operator. In this example, we compare the WT dot tile radius and WP dot mol built-ins, although user defined at the rate reduction operation may be used. Okay, also the range, giving the range of the tile and use performing the reduce operation. Example of is small fusion EMLB approximation of the 2D fluid simulation. Mm, Upper is the original image and lower is the bottom output of 4 layer EMLB after approximation of 1 minute of the training. When you look there, these two images, there is not much difference except for the quality of this is high and this is bit lower, but given this is the output of the training of the approximately 1 minute, we can see that it has the huge there is the huge performance in the uh, using the RAF. Case studies. What are the case studies of the RAF? Tile-based programming also allow for the efficient implementation of fuse multi-layer processing. Below given example of fuse EMLB using the tile-based programming. We are defining the dimension in input, output, and hidden. Defining the using the undecorated in the function as usual. Obtaining the index of the tile. Construct this simple positional encoding using the sine and cosine. Tile breaks the box to create the feature vector and fully connected tile. Loading the tile, mapping the tile, and we are again loading the tile and doing the matplotlib with the mapping the tile with the by doing the matrix multiplication and doing the ReLU operation there. And we are calculating the sum. We are calculating the loss function, and they are doing the atomic add to add the loss. In this example, EMLP fuse kernel implements the two simple two-layer neural network by loading the weight, performing the matrix multiplication, applying the activation function to the using the WP dot tile map and computing the loss within the single kernel. The following image shows the example of this approach to encode the image. Since RAS support the automatic differentiation, we can evaluate and train networks to learn the function image coordinate from the image coordinate xy to pixel RBG. Signal processing reptile. Now let's look at the signal processing. Reptile operation integrates the QFFT-DX in kernel forward and inverse FFT, providing the efficient Fourier transform operation on tiles of the data. Here is an example of the tile-based FFT to compute the convolution using the simple filter. Simple. They are simply loading the filter, performing the FFT in the tile, and computing the filter in the frequency space by mapping the probability and given the Fourier transfer. Computing back to the real number. In this example, CANB tile kernel performs the forward FFT of the forward Fourier transfer of the tile of the data among the last dimension, applies the filter, then compute the inverse FFT. Under the hood, QFFT-DX is used for the implementation. The fault code is example here given here, and the here shows the applying on the noisy input. When given to the noisy input, we can smoothen out the kernel. You can see there is the noisy given the signal list, there is used too much noise here, and green line, it is represented by the smooth image which we want to decode the original signal from the noisy response. For robot forward dynamics, style based programming is highly beneficial for the simulation application where dense linear operator is required. In the remote simulation, the composite rigid algorithm is used to compute the forward dynamics for the articulated system. In the CRPA method, the following triple matrix multiplication is required, where the inner matrix M is block sparse diagonal matrix. It's simply like the SVD, single value decomposition. If you have read it, you may understand it in that way. Once the construction, the system matrix is decomposed using the causality decomposition and solved using the forward and back substitution, which can extract the best version of this program, taking advantages of EM using the wrap primitives. Here is the code. You can go through it. In this example, forward dynamics kernel CRBA method by loading the tiles of the Jacobian and mass matrices and computing their product to form the system matrix H and Cholesky factorization. I don't know how to pronounce it. Cholesky factorization. While TOS require the launching of the dozen kernels in particular use case, the trap implementation require the single fully fused kernel. This reduces the amount of global memory round trips and launch overload, leading to the better performance. Here is the graph between the performance of the under 24 code draft robots is as follows for the dynamic kernels running on the NVIDIA A180GB GPU with all timing in a millisecond. And for the result, lower is the better. Here is the wrap. And here is the wrap plus tile. You can see a tile based approach, it is much lower. Future development. What will be the future development of the wrap? Additional support for the row wise reduction operation, which is nice. Tile creation from the lambda function. Data type and layout conversion, improved performance for the GMN operation, additional linear algebra primitive and induce, including the various metric decomposition algorithm. Tile based programming in RAP 1.50. Wow, provides the powerful and flexible approach to the GPU programming, enabling the developer to achieve the significant performance improvement in their application by leveraging the CUDA-BLAS and CUFFTDX. RAP allows the seamless fusion of GMM and FFT operation, reducing IO and memory kernel launch overhead. You can simply install the RAP in the Python using the pip package of pip install raplang. To run the fuse MLP example, we can python.m. Python.m is means the running Python is running this application, Python application directly. Python.m, a python-m wrap example wrap.examples.tile.example-mlb. Today this much. I get to know about the web programming, and it is pretty much nice. It is intuitive to provide the Python platform to do the GPU based programming and tile based programming, which is very effective and can be used in many can be used along with many other packages to enhance your workflow. That's it for today. Thank you.